Hey guys, Dr. Brown with Kubo Math coming to you from Tarlac City, Philippines. And tonight we have a differentiation problem looking at rates. We've looked at rates before, but this one is a word problem where we have a swimming pool that's being filled at 1/4 cubic meter per minute. Okay, there's 1 meter of water in the pool. And the pool total height is 3 meters. Total width of the pool, or we'll call that the length of the pool, 12 meters. At the shallow end is still 1 meters of vertical space here. You can see this side slopes up to that 1 meter from the 3 meter spot. If you come to this side, you're looking at the pool, it's 6 meters wide. So 12 meters long, 6 meters wide, 3 meters deep at the deep end, 1 meter at the shallow end. Okay, what percent of the pool is filled? We've got 1 meter of water. Okay, well, why don't we figure out what the total volume of the pool is, and then figure out the volume that's associated with the water that's in there. And then we can divide what's filled by the total. It'll give us the percent of the total volume that's taken up by the water that's in there. Okay, so I could say, well, the volume total would be associated with the volume of that triangle. We know we have this, I'm going to call this the base of the triangle, and then we have this length of it. Well, that's of the water. All right. Let's think about this. Let's divide this into different sections. I'll get to the water in a moment. If we look at this 1 meter, there's a rectangle that's associated with that goes across 6 meters. So I could say that's the volume that's associated with the rectangle. So I have a triangle volume and a rectangle volume. Now, since we're looking at total volume, the triangle that we're looking at would be this base here, which is 3 minus 1. So this is 1 meter here, right there. Well, 3 minus 1 gives me 2 meters right here from that spot to there. So the base of that triangle is 2 meters. So my volume of the triangle would be the area times its width. So I'd have 1/2 the base times the height times the width, with the base being this portion here and the height being this. Plus let's see, on the volume of the rectangle then, we've got 1 meter here, 1 meter times the 12 meters times the 6 meters wide. So in this case, 1/2 my base, which was 2 meters, times its height, which was 12 meters, times its width, which was 6 meters, plus all of this, and this is 72 cubic meters, and 6, 12, the 2's cancel, okay, that's 72 also. So I have 72 meters cubed plus 72 cubic meters, and that equals 144 cubic meters. So that's the total volume of the pool. Now then, let's try to calculate what the portion of the pool that's taken up by the water that's in it. Well, I have, again, if I did the volume, 1/2 the base times the height, I don't know what the height is, times the 6. So I know everything but h. But we can do like triangles. Let's see, I have the height, we'll say h, I'll put it down here. H is to 1, and these are all in meters. H meters is to 1 meter. So this is to 1, as 12 is to 2. As 12 meters is to 2 meters. Obviously all the meters cancel. So I end up cross multiplying. So 2h equals 12. Divide both sides by 2. So h equals 6. So this distance right here is 6 meters. Hey, now we're in business. Okay, so the volume that's filled, I'll fill in that triangle. Volume that's full of water is 1/2 its base of 1 meter times 6 meters times the width, which was also 6 meters. Oh, that was not cubed, 6 meters. So now I've got 6 times 6 is 36. So I've got times 1 is 36 cubic meters divided by 2 gives me 18 cubic meters. And that's the volume. I'll fill that in of what's full, that triangle that's full. So now the percent filled, so the answer to my first question up there would be the volume that's full divided by the volume total. So that's 18 cubic meters divided by 144 cubic meters. Well, what do we got here? We've got, let's go old school. All right, we have 2 times 9, which is 3 times 3. That's cubic meters. Well, the cubic meters is going to cancel, so we'll just leave that off. So 2 times 3, 2 times 9 is 18. That's 2 times 3 times 3. So 144 is 12 times 12, which is 2 times 6 times 2 times 6. So 6 is 2 times 3 times 2 times 2 times 3. All right, old school math here. The 3's cancel, these 3's cancel, that 3 cancel. So I have 1 over 2 times 2 is 4 times 2 is 8. The pool is 1/8 full, and that's 12.5%. So this first one, what percent of the pool is filled? 12.5%. Okay. Now let's move on to the next question, and it says, at what rate is the water level rising? Now you'll notice they have a few tricks in this problem. The geometry associated with this rectangle that goes across the pool there doesn't come into play because the water hasn't gotten to that level. The water level rate, or water height of this water, and we're calling that our base, by the way, that thing is raising with just associated with the triangular features. So we need to keep that in mind then as we work through this. So the volume associated with that portion of the pool, and keep in mind we're dealing with the big triangle now. So we're looking at the volume, and that volume is 1/2 the base times the height times the width, with the base being this portion of the triangle. So that's the one we want to differentiate. So we're going to take the derivative of the volume with respect to time, and that equals 1/2, I'm going to HW, they're constants, times dB dt. The rate of change of this base, the rate of that water is rising with respect to looking at the change of the volume with respect to all of this. Now, we know the volume is changing at 1/4 cubic meter per minute. So we already know what this is. The only thing we don't know is dB dt. So we're looking at dV dt divided by 1/2 H times W, and that equals dB dt. Well, what does that equal here? All right, so we've got 1/4 cubic meter per minute divided by 1/2 h, which remember we had h is 12 meters, times 12 meters times our width, which was 6 meters. Okay, so that's 72 square meters divided by 2 gives me 36. So I end up with 1/4 cubic meter per minute divided by 36 square meters. So one of the meters cubed divided by meters squared leaves me meters. So I end up with 1/144 meters per minute is the rate at which this height of water, we called it our base, was changing. So it would take, what would that be, 144 minutes to go 1 meter. So 144 minutes, so almost 2.5 hours, 2.4 hours to get this thing to fill up from where we are currently to here. I guess you turn your water hose on and come back later. Now obviously once we get to the point where the geometry changes, the rate at which it's filling changes also. So in this case we've got 1/144 meters per minute is the rate at which the water is rising in the pool when when the base is currently at 1 meter. That changes if the height is different, but at that moment that's when it's 1/144 meters per minute. All right. That's a nice little problem. Some geometry considerations, they try to throw you off with the different features here, and you just have to back up and say, what are they really asking, and work through it. Okay, why are we doing these things? We're trying to practice so that we can build a better tomorrow. That's what we're trying to do, and do that how? Through math. Learn new skills and just keep practicing. Okay, that's all for now. Hope you enjoyed it, and we'll talk to you next time. Thanks.